The God particle is a nickname for the Higgs boson, an elementary particle in the Standard Model of particle physics. It was theorized by Peter Higgs and others in the 1960s and later discovered in 2012 at the Large Hadron Collider (LHC) at CERN. The Higgs boson is associated with the Higgs field, which gives mass to other particles. Without this field, fundamental particles would be massless, and the universe as we know it couldn't exist. The name comes from the title of the book, The God Particle. If the universe is the answer, what is the question? By Leon Lederman. The story goes that Lederman originally wanted to call it the goddamn particle due to the difficulty of detecting it, but the publisher changed it to God Particle for marketing purposes. The nickname stuck, despite criticism from scientists, as it sensationalized the particle's significance. Mass generation. The Higgs boson is a key part of explaining why particles have mass. Without it, the Standard Model would fail to describe reality accurately. Validation of the Standard Model. Its discovery confirmed the existence of the Higgs field, supporting the Standard Model's framework. Cosmological implications. Studying the Higgs boson helps scientists understand the conditions of the early universe and could offer insights into dark matter or even the ultimate fate of the universe. Fire theological and philosophical implications. Despite its nickname, the Higgs boson has no direct connection to God or theology. However, its discovery sparked philosophical and metaphysical discussions. Some view it as a window into understanding the fine-tuning of the universe, while others see it as evidence of a deeper naturalistic mechanism behind existence. The name, God particle, evokes the mystery of creation, but it's purely a scientific term. The Higgs boson itself is not something that can be directly seen, since it's a fundamental particle, but scientists can visualize its detection through data representations. When it is produced in a particle collision, it quickly decays into other particles, and the detectors at CERN's Large Hadron Collider (LHC) capture the traces of these decays. Cyclone visual representation. In the visualizations from LHC, the collision point is at the center of the image. The decay products, photons, electrons, or other particles, shoot outward, creating colorful tracks. The Higgs boson itself is invisible. It is inferred from the decay patterns and energy signatures. H right pointing arrow NG, 2 photons. This produces 2 energetic photons, visible as streaks in the detector data. H right pointing arrow ZZ right pointing arrow 4 leptons. The Higgs decays into 2 Z bosons, which further decay into 4 leptons, electrons or muons, leaving a characteristic track. H right pointing arrow WW right pointing arrow leptons plus neutrinos, another common decay with a specific pattern in the detectors. Would you like to see a scientific simulation or visualization of a Higgs boson event? In a sense, the Higgs boson, or more accurately, the Higgs field, plays a fundamental role in shaping the universe as we know it. It doesn't power the universe in the way a star or energy source does, but it enables matter to have mass, which is essential for the formation of galaxies, stars, planets, and life itself. Particles like electrons, quarks, and WZ bosons interact with the Higgs field, which gives them mass. Without mass, particles would zip around at the speed of light, preventing the formation of atoms and larger structures. The Higgs field also influences the stability of the vacuum. Some theories suggest that the Higgs boson's precise mass could determine whether the universe is in a stable or metastable state. If metastable, the universe could theoretically collapse in a distant future. Vacuum decay. The Higgs field is present everywhere in space, but it doesn't power the universe directly. Instead, it's part of the quantum fields that define how particles interact and behave. While the Higgs field gives mass to regular matter, it does not explain dark matter or dark energy, which make up about 95% of the universe. Some theories propose that the Higgs boson could have interactions with yet undetected particles, offering potential clues to dark matter. You could think of the Higgs field as a kind of invisible cosmic ether that shapes the fabric of reality, allowing the dance of particles to form the tapestry of existence. Without it, there would be no stars, no planets, no life, just a sea of massless, speeding particles. The Higgs field itself is believed to be infinite in extent. It permeates all of space-time. It's a scalar field that exists everywhere in the universe, even in the vacuum of empty space. This is why all particles with mass constantly interact with it, no matter where they are. No, The Higgs boson is not infinite, it's a finite, elementary particle with a specific mass of about 125 giga-electron volts, GeV. When particles like protons are smashed together in the LHC, the Higgs boson appears for a fleeting moment before decaying into other particles. Its existence is extremely brief, on the order of 10 squared seconds. The Higgs field stretches across the universe, making it effectively infinite in range. The Higgs boson is a localized ripple or disturbance in this field, making it finite. You can think of it like the ocean and a wave. The ocean, the field, is vast and ever-present, while the wave, the boson, is temporary and limited. Some physicists speculate that the Higgs field could have different values in different regions of a hypothetical multiverse. In other words, the Higgs field might not be identical or infinite across every possible universe, suggesting that other universes could have entirely different physical laws. The Higgs boson itself doesn't have any direct, practical uses, it decays too quickly to be harnessed. However, the discovery of the Higgs boson and the study of the Higgs field have profound implications for both science and technology. Understanding mass and gravity, the Higgs boson helps scientists understand how particles acquire mass, which could lead to deeper insights into the nature of gravity, a force that still lacks a quantum explanation. Probing the universe's stability, studying the properties of the Higgs boson helps physicists explore whether the universe is in a stable or metastable state, which has implications for cosmology and the ultimate fate of the universe. While the Higgs boson itself isn't used for technology, the research at CERN, which led to its discovery, has resulted in major technological advancements. Medical imaging, technologies used in the Large Hadron Collider, LHC, such as advanced detectors and imaging systems, have applications in PET scans and cancer treatments. Particle accelerators in medicine, particle physics research contributes to the development of proton therapy, which targets cancer cells with precision, minimizing damage to surrounding tissue. Data science and AI, CERN's need for handling vast amounts of collision data has driven advancements in machine learning, data processing, and the development of the World Wide Web, which originated at CERN. Some theories suggest the Higgs boson might interact with dark matter particles. If so, studying it further could lead to discoveries about this elusive substance that makes up 27% of the universe. It might also provide clues about dark energy, the force driving the accelerated expansion of the universe. The Higgs boson could open doors to discovering new fundamental particles or forces. Some theorists believe it could be linked to supersymmetry, SUSY, a hypothetical theory that could explain why particles have the masses they do and possibly reveal a new family of particles. While not a usable particle in the practical sense, the Higgs boson holds existential significance. It reveals the underlying fabric of reality. It challenges our understanding of the origin of mass and existence itself. It brings us closer to answering questions about the early universe and the conditions that led to our existence. One of the biggest mysteries in physics is the lack of a unified theory that combines quantum mechanics, which governs particles, with gravity, which governs space-time. Mass and space-time curvature. Since the Higgs field gives mass to particles, it indirectly influences how gravity acts on them. In a sense, it links mass and gravity at the quantum level. Some speculative theories propose that the Higgs boson could interact with a hypothetical graviton, the quantum particle of gravity, potentially revealing quantum gravity effects. Extra dimensions. The Higgs boson might provide clues to the existence of extra dimensions. Certain models, like string theory, predict that the Higgs could interact with particles that travel through extra dimensions, offering a glimpse of a deeper reality. Cosmic inflation refers to the rapid expansion of the universe in the first 10 cubed to the power of 6 to 10 cubed squared seconds after the Big Bang. Some physicists speculate that the Higgs field may have played a role in this process. The particle responsible for driving inflation is called the inflaton, which is hypothetical. Some theories suggest that the Higgs field itself could have acted as the inflaton, expanding the early universe. Vacuum instability and cosmic fate. The Higgs field may determine whether the universe is ultimately stable or metastable. If metastable, the vacuum state could eventually decay, causing the entire universe to collapse in a false vacuum decay billions of years from now. While there is no direct link between the Higgs boson and consciousness in mainstream science, some theoretical physicists and philosophers have speculated about potential connections. Quantum fields and consciousness. Since the Higgs field pervades all of space, some philosophers have speculated that consciousness might arise from interactions with fundamental quantum fields. While this is purely speculative, it echoes panpsychism, the idea that consciousness is a fundamental property of the universe. The observer effect. In quantum mechanics, observation seems to collapse wave functions, creating a reality we experience. Some interpret this as a link between consciousness and quantum phenomena, but there's no evidence the Higgs boson directly plays a role in this process. Mystical interpretations. Some spiritual or philosophical interpretations view the Higgs field as a cosmic fabric that connects everything. While not scientific, this notion mirrors ancient pantheistic or panentheistic ideas, where all of reality is seen as interconnected and divine. In a metaphorical sense, the Higgs boson is like the invisible hand that gives form to existence. It imbues particles with mass, making the universe tangible. Without it, there would be no matter, no stars, and no beings to ponder the mysteries of reality. Quantum gravity aims to unify general relativity, gravity, with quantum mechanics, but so far, the two frameworks don't fit together. The Higgs boson could play a role in solving this puzzle. String theory proposes that all particles, including the Higgs boson, are actually tiny vibrating strings. The Higgs boson could be a vibrational mode of a fundamental string. Some versions of string theory suggest that the Higgs field might interact with hidden extra dimensions, beyond the familiar 3+1 dimensions, 3 space plus 1 time. If true, experiments could detect deviations from the standard model caused by the influence of these extra dimensions, potentially revealing the quantum nature of gravity. Checkmark why it matters. If string theory is correct, the Higgs boson might provide evidence for extra dimensions or even new forces that could bridge the gap between quantum mechanics and gravity. Another candidate for quantum gravity is loop quantum gravity, LQG. It describes space-time as made of tiny quantum loops rather than a smooth continuum. The Higgs field might interact with the quantum loops that make up gravity. This could cause subtle deviations in the behavior of particles at extremely small scales, offering clues to quantum gravity effects. Checkmark why it matters. If LQG is right, the Higgs boson could indirectly reveal evidence of space-time being made of discrete quantum loops, reshaping our understanding of gravity. Milky Way 2. Cosmic inflation and the Higgs field. The inflationary model suggests that right after the Big Bang, the universe underwent a brief but rapid expansion. Some theories propose that the Higgs field itself may have driven or influenced this inflation. The inflaton is the hypothetical field responsible for cosmic inflation. Some physicists propose that the Higgs field could have doubled as the inflaton, driving the early universe's rapid expansion. If true, this would explain why the universe appears flat, homogeneous, and isotropic today. Checkmark why it matters. If the Higgs field was the inflaton, its properties would be directly responsible for the large-scale structure of the universe. The mass of the Higgs boson, approximately 125 giga-electron volts, suggests the universe might be in a metastable state, not a perfectly stable one. The vacuum state of the universe could eventually decay into a lower energy state. This false vacuum decay would trigger a bubble of destruction expanding at the speed of light, wiping out everything. While this is an extremely remote possibility, trillions of years from now, it has philosophical implications about the universe's ultimate fate. Checkmark why it matters. The Higgs boson's mass could determine whether the universe is destined for eternal stability or eventual decay. While not directly linked to consciousness, some theoretical ideas suggest that fundamental fields like the Higgs field could play a role in shaping the conditions for consciousness to arise. Panpsychism suggests that consciousness is a fundamental property of the universe, existing at all levels, even in particles or fields. Some philosophers speculate that the Higgs field, being omnipresent, could play a role in the fabric of reality in a way that supports or generates awareness. Though highly speculative, this view echoes ancient pantheistic or panentheistic ideas, that the entire cosmos is alive, with some form of consciousness. Checkmark why it matters. While not a scientific claim, exploring whether quantum fields could be tied to awareness challenges the traditional divide between physics and consciousness. In quantum mechanics, the observer effect suggests that observation collapses wave functions into definite states. While the Higgs boson itself doesn't play a role in this, some theorists wonder, could the Higgs field be linked to the underlying fabric of quantum reality? Could it interact with the quantum vacuum in ways that influence how reality manifests? Check mark why it matters. Although there's no scientific evidence, these speculations touch on the metaphysical nature of reality and the mystery of how the universe manifests into a concrete form. Milky Way 4. In a poetic sense, the Higgs boson could be seen as the cosmic sculptor. The Higgs field gives mass to particles, turning them from mere energy ripples into real matter. Without the Higgs field, the universe would be a sea of massless, speeding particles, no atoms, no stars, no life. Its omnipresence makes it feel almost divine in nature, echoing spiritual concepts of a universal force that gives form to existence.